So, so good afternoon, everyone, and welcome to a fresh new session of credit risk modeling development using SAS. Uh, so, just a couple of things before I start off. So, is my screen visible, and can you hear me, guys? Am I audible? Great. Okay. So just a quick couple of things. So, I was not able to share the recordings for the last session with you guys, right? So I'm still in the process of uploading your look. The other batches on the Google Drive. So I believe I'll be able to complete it by tomorrow. Expect the link for the Google Drive tomorrow, and in case you don't get it by Monday, just send me a reminder mail. I'll do it at the earliest, right? So that's one thing. Second is that Prakash has suggested creating a WhatsApp group among the team so that things could be discussed easily. So I believe that's a fantastic idea. If people could share their contact details, Prakash could actually take it up, right? Okay, so that is one thing. So if you guys could share your contact details with Prakash over this chat box, I think Prakash can quickly create the group if required after the class today. So we'll just take up the discussions from the point where we left off in the last class. So, so just before I move on, a quick round of discussion, right? So basically, we started off discussing about the overview of the module, right? So we had discussed that there are broadly three basic approaches that we would actually talk about, right? So first is so broadly from the functional perspective, there are two broad topics. Number one is business scorecard development, and the second is the regulatory model development. So while we talk about business scorecard development, we would be basically talking about application scorecard and behavior scorecard development. While we talk about regulatory models, we will be talking about a lot of different regulatory models, but we would have PD, LGD, EAD, and the provisioning models at the heart of it, right? Now, from there, we started talking. We said that to have an understanding of the modeling techniques, one broad method that we need to understand are the statistical procedures, the statistical sections. So out of this, the basic stat. So therefore, we started discussing about the basic statistical sections, right? So first of all, we had agreed that we would start off by discussing the statistical sections, the section on statistics, which will cover a detailed description of descriptive statistical models, inferential statistical models, and predictive statistical models, right? And using that, we would move to analyze the application and the behavior scorecard first, and followed by the regulatory model development of PD, LGD, EAD, etc. Now, from there, the next part, so what we had discussed in the last class mostly was methods which included the basic descriptive measures, like the measures of central tendency, the measures of dispersion, and the measures of asymmetry. Also, within this part, the section that we had talked about was the basic descriptive measures, which incorporated both absolute measures of central tendency and as well as the relative measures of central tendency, where we had discussed about mean, median, mode, and relative measures like percentiles, deciles, etc. One major conclusion that we had created from our discussion over there was that the absolute measures of central tendency often tends to get biased by the existence of outliers, whereas the relative measures of central tendency do not get that. And by comparing the basic measures of the basic descriptive measures like mean, median, and mode, we can actually frame out an idea about the distribution of a given variable. So this is what we had discussed in the last class. So So that is the part that we started off our discussions with, right? So in today's session, what we'll do is we will continue our discussions along the same lines, and we will be talking about different. So we'll be talking about the descriptive measures in greater details. And like we had discussed about measures of central tendency. So apart from measures of central tendency, we would also talk about the measures of dispersion as well as measures of skewness. And our objective would be to understand how best can we frame an idea about, or how is it that we can actually go about developing, or how best can we go ahead developing the models using these techniques. So what different insights would they give us? What are the key types of averages that we generally have while we are working? Great. Just a moment. Okay, so can you hear me now, Srini? Hello. Okay, great. So so we'll start off with a greater detailed discussion on the measures of central tendency. Now, when I talk about the measures of dispersion, the measures of the descriptive measures, right? So we would not only be talking about the basic measures. So we would be talking about the different measures of central tendency, dispersion, as well as asymmetry. So in the last class, we had just introduced the basic measures of central tendency, and we said that there are two types of broadly, there are two techniques. One is the absolute measures. The second is the relative measures of central tendency, and so on. From today's session, what we'll talk about is we'll delve more deeper into each of these concepts. Even though I'm aware of the fact that mean, median, and mode are something which is conventionally known to all of us, right? But again, there are certain intricacies, there are certain nuances that we need to focus on from the perspective of framing data insights, right? So one basic, dependent on the variables that we have, right, the measures of central tendencies start changing. So talking about the first broad measure of central tendency, which is mean. And mean is something which we all are very well aware of. And we know that mean is nothing but it is the sum of the observations divided by the total number of observations. But that is only one type of mean, right? So, and that the most common type of mean that we work around is called the arithmetic mean, or as we call it, AN. AN. AN stands for arithmetic mean, and it is represented as, we define it as 1 divided by n summation xi, right? And this value xi, 1 divided by n summation xi, is called x bar. So this is something we represent, and this is the most commonly used form of mean that we generally talk about, right? Also, this is known as the x bar a, or arithmetic mean. The next thing that we need to understand is the second type of mean, which is called the geometric mean. The geometric mean. So what is the geometric mean like? The geometric mean is nothing but the nth root of the n observations that we have. So x1, x2, up to this at the nth observations. So to the power of 1 by n. So it's the nth root of the n observations, and is also called the x bar g, or the geometric mean. Now, the third type of mean that I have is called harmonic mean. Now, what is harmonic mean? The harmonic mean is the reciprocal of the mean of the reciprocal of the observations. So it is basically defined as, for a set of n observations, is defined as 1 divided by 1 by x1 plus 1 by x2 1 by xn. So this is called the harmonic mean. Now what becomes important is, irrespective of the data sets, we always try, we just go about and just, we just use arithmetic mean very indiscriminately. But again, arithmetic mean or usage of arithmetic mean has its own limitations. So there are certain cases where arithmetic mean may not be a very effective measure, but still arithmetic mean is the most widely used measure of central tendency. So it's one of the most widely used measures among these three groups of means. This is widely used. Now the reason is why. So arithmetic mean obviously has a set of disadvantages as well as it has a set of advantages. So the biggest advantage that arithmetic mean has is that it uses all the observations for calculation of the mean. Therefore, it is a very wholesome representation of the average of the overall of the central behavior. But again, at the same time, the challenge that comes up is that if the observation, if one or more of the observations are very different from the rest of the data set, so if there is an underlying heterogeneity in the data behavior of the data, then arithmetic mean becomes questioned, or there are certain sort of questions which arises. So in order to solve that, there are other alternate measures of mean which has been proposed. So basically, while we talk about using arithmetic mean, we need to understand that when is it that the mean, the arithmetic mean needs to be used. So, so basically, arithmetic mean is used if a series of observation is in arithmetic progression. If a series of observation is in arithmetic progression, is in AP. So basically, if it does not follow a geometric progression, or if it does not increase at a given constant rate or anything, if the series is a simple arithmetic progression, then I'll say that yes, this series or this variable can be covered by or can be represented by a arithmetic mean. Similarly, if a series has a geometric progression, so if a series is in geometric progression, then what I have is it will be the geometric mean will be used. The series is in geometric progression. Now, the question that comes out is that I'm saying that if a series is in arithmetic progression, then it is used. Then arithmetic mean is to be used. Whereas if my series is in a geometric progression, then I'll use a geometric mean. So the question that comes out is, what if I use arithmetic progression in a series which follows geometric progression? So what if I use AM or arithmetic mean to represent a series in geometric progression. So to answer this, the first question that I need to get is that what exactly is geometric progression? The series is in GP. So the first question that comes out is what is a geometric progression? So a geometric progression is a series where a series grows at a constant rate, right? Say for example, I have a principal of rupees 100 which I have deposited in a bank, right? So I have a principal of rupees 100 in a bank, right? Now every month or every year there is a rate of interest of 4%. So there is a rate of interest of 4% per annum, right? Now what I want to know is that what is the amount that I'll get at the end of 1 year. So amount at the end of 1 year. So what will be the principal? So the amount is 100 plus the 4% of rupees 100, right? So that is 0.04 into 100. So that is nothing but 104. So at the end of 1 year, what I get is 104. Now, what I want to also know is that at the end of the second year, if the same story continues, what is the amount that I will have? Now, when the second year begins, this 104 becomes the principal, right? And on top of this 104, you get another principal of 104. I mean, and you get another rate of interest of 4%. So basically, the amount at the end of the second year will be 104 plus 4% of 104 into 104, right? So now what I can write over here is this is nothing but 104 into 1 plus 0.04, right? Now this 104 itself is nothing but 100 into 1 plus 0.04 and again 1 plus 0.04, right? Now if I write this statement, then what happens? What happens over here is I can see that at the end of 2 years, the amount is nothing but the principal P100 into 1.04 square. So what you can see over here is that every time, so as the years go by, the amount is going to increase by an amount or by a value 1.0.04, that is into 1 plus r. So every year 1 plus r is getting multiplied to get the total amount. So therefore what you can see is that this amount is increasing proportionately, right? So this growth is called a geometric growth, and all these observations 100, 104, then 104 into 1 plus 0.04, like these, all these values are said to be in a geometric progression. That is, from as I move from the first to the second, I just multiply a multiple, a constant multiple. I get the second value. As if I want to move from the second to the third, I again multiply that constant value. So again, in the next part, what I end up with is the third observation. So it is in this way that the observations keep on increasing gradually. And this type of a series is called a geometric progression. For example, a very simple example of geometric progression, therefore, is the compound interest. Is the compound interest. Say for example, if your interest is getting compounded annually and you want to find out what is the average rate of interest that you have earned, the amount in order to find out that average interest, you are not going to do this thing. So you are not just going to do an arithmetic mean of the interest values. What you need to ideally do is you need to do a geometric mean of the interest values, because all the observations are in a compound interest will be in a geometric progression. Say for example, it is principal. The second part is principal into 1 plus r. The third term of the series will be principal into 1 plus r square. So what you are getting to see is a stream of the amounts that the person is likely to get. And every time, in order to move from this point to this point, what you are doing is you are multiplying a 1 plus r. Right, so again to move from this point to this point, you are again using this 1 plus r. Right, so every time you are multiplying a constant value, right, a constant multiple, and you are actually moving from one point to another. So this type of a series is said to be in a geometric progression. So where there is a constant rate of growth, if something is growing in a constant at a constant rate. So if something is not constant but it is growing at a constant rate, right? So this is called geometric progression. Clear? Okay. Sorry. Anirudh? Great. So now the question that comes out is that what if I use, so I have said that if a series is in a GP, the mean that I will compute is what, or would be a geometric mean. Right. Now the question that comes out is that why is it that I will use a geometric mean? Why not an arithmetic mean? So if a series is in a geometric progression, why is it not correct to calculate a arithmetic mean? So this is the reason. So let's start thinking with two observations, right? So say suppose I have two observations, x1 and x2. So for these two observations, arithmetic mean will be nothing but x1 plus x2 divided by 2, right? And going by the definition of geometric mean, Geometric mean should ideally be root over of x1 into x2, because it is x1 into x2 to the power of 1 by n. So over here n is 2, therefore geometric mean is nothing but x1 into x2, right? Now what I'll do is I want to understand that, so if arithmetic mean is different from geometric mean, then there will be a problem, right? However, if arithmetic mean and geometric mean are equal, then it hardly matters whether I use an arithmetic mean or a geometric mean to find out the average. So if I am using geometric mean in a geometric series, then what it means is, or in a series which is geometric progression, then what it means is that using arithmetic mean will give me a different value. That is why I don't want to use. So that is what I'm going to check out over here. What I'm going to check out over here is arithmetic mean and geometric mean different in terms of their values. So obviously let's just find out, we're just trying to find that part out. So let's do a very simple subtraction. Okay. I'll say am minus gm. Now if am minus gm is not equal to 0, then it will mean that these two will give me different results. However, if I can prove that am minus gm is equal to 0, then it means that am and gm are equal, are the same value. That's why their difference is equal to 0. So let's have a look into this. So over here x1 plus x2 divided by 2 minus root over x1 into x2. So this is what the value is, right? So now if I calculate this value, what I'll get is x1 plus x2 minus 2 root x1 x2 whole divided by 2, right? Now how can I represent this part? So this equation can be represented as x1 is nothing but root x1 square. Square root of anything, I mean the square of the square root of anything is nothing but the number. So basically if I have a number 2, I can always write it as root 2's square. Similarly, x2 can also be written as root of x2 square minus 2 into root x1 minus x1 into x2 whole divided by 2. So this can also be written as, so this is a square plus b square minus 2ab. So this is nothing but a minus b whole square. So this is nothing but root x1 minus root x2 whole square by 2. Now, since the numerator is a whole square can never be negative. So all it can be is greater than equal to 0. Therefore, what I can say is that a minus gm, this difference is nothing but greater than equal to 0. That is am is greater than equal to Gn, and the equality will hold only if x1 and x2 are the same values. So if x1 is equal to x2, then this difference holds with equality, else am is greater than gm. So since arithmetic mean is greater than geometric mean, what it implies is that if for a geometric series I use arithmetic mean, I will be overestimating the mean. So if I do this, I will be overestimating the mean. I will be overestimating the mean. Overestimating the mean. Right? So this is the reason why if a series is in a geometric uh, progression, then it should always be averaged using geometric mean. So that is what we have over here. Right? So since arithmetic mean is greater than equal to the geometric mean, therefore if for a geometric series, if we are averaging it using the arithmetic mean, then what we would be doing is we would be ultimately overestimating the mean of the series. Hence geometric mean needs to be used. But still, there are cases where for even for geometric series, right, say for example your portfolio grows at a constant rate, right, and you want to average the receivables growth rate, that you want to find out the average growth rate. What you do is you do an average, you do a, you know, you do a arithmetic mean, and you know that it might actually overestimate the average, but still you go and do it. Why so? Because geometric mean as as a measure of mean has two very severe limitations. One of the limitation that we have over here is that if any xi, so for any ith observation is equal to 0, then the entire geometric mean is 0. Now if I'm averaging growth rate, there might be a value which is rounded up to two figures, two decimals, the figure is 0, right? Then the entire geometric mean will turn out to be 0 because it is always recorded in a multiplicative format, right? So similarly, another very important limitation of geometric mean is that if we have a geometry, if there is a xn which is xi which is negative, geometric mean will become imaginary. So if any xi is less than 0, then geometric mean will not belong to the real space. It will belong to the Z space, or it will belong to the imaginary space. Therefore, these are the two basic limitations. Now, even talking about growth rate, there can be a period where there was a negative growth. So that is, there will say the portfolio has shrunk and the growth rate is recorded as minus 0.2%. Then in that case, it will become a big challenge to compute the geometric mean, because if there is a negative value, right, so if there is a negative value, the product of the geometric mean with the nth root will become imaginary, and it will not belong to the real line. So the geometric mean will become an imaginary value, because generally if we have, say, a root over of minus value, say minus 0.05, right? So this is a imaginary value. So this is a imaginary set or an imaginary value, right? And it does not belong to the real line or to the real space. So this is what we call the real space. Real line. Clear? Okay. So this is a challenge related with geometric mean, which is not for arithmetic mean. Whether you have, minus values or zeros, whatever it is, arithmetic mean will give you the average value, because it's an additive function, whereas the geometric progression is a multiplicative function, right? Right? Everyone understood? Prakash, Anirudh, Srinivas. Great. The next part that we need to talk about is harmonic mean. Now, harmonic mean is something which is, a harmonic mean is something which is used to average variables like speed. You want to understand what is the average speed of a car, what is the average mileage of a car. So basically, you are looking into variables like x per unit of y, meters per second, kilometers per liter, right? Kilometers per hour, miles per liter, etc. So you are looking to have these values. So when you are looking to use these values, or you want to create an average of such values, harmonic mean is something which is used, right? Now, harmonic mean as a mean measure or as a averaging measure has a very important characteristic. It gives the highest weightage to the lowest value and the lowest weightage to the highest value. So basically, if your economy, say for example, if your data set has a couple of outlier values and you want to minimize the impact of those outliers, then what you can do is you can actually think of using harmonic mean to do that, right? However, your variables must be in the appropriate frame or must be in the appropriate format required for using harmonic mean. So basically, if I'm trying to use harmonic mean, what I'm trying to do over here is I am trying to average variables which are in the units of, like, say, x per unit of y. X per unit y. Okay. So basically, harmonic mean gives highest weightage to the lowest value and lowest weightage to the highest value. weightage to the lowest value. Value and lowest weightage to the highest value. So I'll put it as and vice versa. And vice versa. So highest weightage to the lowest and lowest weight to the highest. So basically this distribution will be very useful for averaging skewed distributions. For averaging skewed distribution. Averaging skewed distribution. And this is where this variable actually scores over the arithmetic mean. So what arithmetic mean does is arithmetic mean gives a higher weightage to a higher value and lower weightage to a lower value, or equal weightage to all the values. However, if there is a huge extent of asymmetry in your distribution and you want to get a more representative picture, harmonic mean is suggested, provided that you can write out your distribution values per unit of x per unit of y. Right. Say expenditure per unit of money earned or something like that, and then you just income per unit of our work. If you do something like this and then you create the average way, then you try to create an average, you can actually use harmonic mean to do that average. Now how does harmonic mean then solve this problem? Let us, for example, take the case that in an economy there are two people. So there is an economy or a country, right? And there are two individuals, A and B, and there are just two individuals. Over here, individual A earns rupees 2 per month. Individual B earns 100 rupees per month, right? Now what I do is I do the x bar A. So what happens is x bar A is 100 plus 2 divided by, this is 102 divided by 2, which is 51. So over here the mean is 51. So you will see that when I have used this mean 51, 51 is more biased towards 100 rather than 2. So 51 is more representative of the value 100 rather than the value 2, right? Because you are giving the same weightage, therefore the higher end value is pulling the average value towards itself. Hence, the average value of this 51 as a representative value is more biased. So the x bar A values are biased. A is biased. x bar a is biased, right? Now if x bar a is biased, right, so what is the alternative that is there? So the alternative over here is x bar h. So what harmonic mean does over here is 2 divided by 1 by 100 1 by 2. So that is 2 divided by 100 is 0.01 and zero point 0.5. So that is 0.51. So 2 divided by 0.51 will be just a minute. That is 3.92. So over here what you will see is that now this x bar h, or the value which is generated by x bar h over here, which is equal to 3.92, is more representative of the lower end values than the higher end values. So over here, this average, you would see that this value is more representative of the lower end values rather than the higher end values, because this is what the the best advantage that this particular method has, right? So the best advantage that this harmonic mean has is this is 3.92. So it's more representative of the lower end values because it gives the higher end values a lower weightage and the lower end values a higher weightage. Clear? So this is the advantage that harmonic mean has over arithmetic mean. So if you have an extremely skewed distribution, you can think of using harmonic mean, provided that the variable values are converted into x per unit y. But at the same time, harmonic mean also has a very big challenge. The challenge that harmonic mean has is, let's say for example, instead of this being 2, I'll keep the same thing, right? So I'll say A earns 0 income and this person earns an income of 102. Now for this income distribution, if you look into the income distribution over here, and if you want to compute the harmonic mean for this distribution, the harmonic mean will not be defined. So the harmonic mean will be undefined, because the harmonic mean over here calculated will be 2 divided by 100. Sorry, it will be 2 divided by 1 by 100 1 by 100 and this divided by 0. So now as I write this part is undefined. right? So therefore, if your series contains a value 0, then harmonic mean gets undefined. So geometric mean in the presence of negative values and harmonic mean in the presence of 0 gets undefined, and geometric mean gets undefined if if at least one of the values are negative. Therefore, even if you know that it is appropriate to use geometric mean and harmonic mean, you may not be able to use them. Rather, it is more, and since arithmetic mean is such a easy to use measure, therefore arithmetic mean is preferred over geometric mean and harmonic mean from practical applications for calculating averages, despite the challenges that arithmetic mean has. So, in order to solve those challenges related to outliers or to extreme values, there are other tests which are done, there are other checks which are done, and those outliers are removed from the data and then the analysis is done. But on the other hand, if we are to use this measure, then it does not happen. Like if you are to use like arithmetic mean is something which is more preferred, and hence all the other data challenges are dealt off with, and then arithmetic mean is used as a measure to represent the overall behavior of the data. So and that is the reason why it's one of the most sought after, one of the most widely used absolute measure of central tendency. Clear up to this point? Is it clear, guys? Just sit through it. Just recollect whatever I have said. Just sit through it for 1 minute. See if there are any doubts, and then we'll carry on. Okay. Okay. Great. So, having said that, the next part is to understand the importance of this measure of the means. So, what are the means all about, and what are these things? So what does the mean try to show, or what does it give us? So basically mean, as we know, gives us the average behavior of a variable. And it is this average behavior which plays the biggest role in predictive modeling, because in predictive modeling, whenever we are trying to model something, we are trying to develop a model, we are always looking into the average behavior. So we are looking into the historical average behavior, and based on that, we are trying to form a prediction of the average behavior in the future. So based on the historical behavior, what we'll have is the future behavior. So this is what we are trying to do. Now, now, now let's see an example as to where this average behavior comes in so handy and what are the different ways of computing this average and all. So let us say that I have a data on income and consumption, right? So say I have a data on income and consumption. There's an income and consumption data which I have. Say, uh, the income framework that I have over here is say 20K. Right, say 21K. $20.5K. Again 20K. 20K. 21K. So I have these values, right? Now along with these values, I also have the consumption values. Say the consumption over here is 16K. Then what I have is 16.5K. 18K. The next over here is 19K. 17K. So 20K. Now observe that there are three readings where the people have exactly the same income. 20K, again 20K, again 20K. But for each of these income, what I get to see is that the consumption patterns differ, right? So corresponding to this 20K, for 120K there is a 16K, there is 20K, 19K, like this. So basically what I get to see is that there is a distribution of consumption corresponding to one given level of income, right? So basically now if someone asks me that what is the consumption of a representative individual who earns 20,000 per month, so what do I say? Do I say 16, 19 or 17? I cannot say it like that. So now if I want to analyze the data, I need to aggregate this. So therefore what I do is I take out these three observations which earn the income 20,000 And for all these three groups of observations, for all these three observations, what I do is I create out an average value. So what I say is that it's 16 plus 19 plus 17 divided by 3. So it is 52 divided by 3. It's 17 point something. So it's roughly 17k approximately. So this 17k that I stayed over here, this 17k is nothing but the expected consumption or the average consumption. The expected consumption or the average consumption. The expected consumption or the average consumption. Clear? So basically, averages are used for prediction. So basically, when I am predicting this based on this value, right? So basically, what I say is that this 16k that I get to see over here, or this observed value that I get to see over here, is comprised of two parts. One is the average behavior, and the other is the random or the uncaptured behavior. Now for prediction, we can only predict the average part. The random part of the story cannot be predicted. So whenever we predict this, when I predict this, so this is the part that I can actually predict, and it is this random part which creates the difference between estimated difference between the estimated and the observed values. Difference between the estimated and the observed values. Clear? So basically, whenever we are trying to predict, so we'll discuss this in greater details when we get into the predictive modeling side of things. So basically, when we are trying to predict something, we are trying to predict the average behavior of the dependent variable based on the average behavior of the historical average behavior exhibited by the independent variable. Clear? So is this part understood? Great. Anirudh, Priti. Okay. Great. Now, having said that, the next part that we'll talk about over here is the different kinds of averages, about arithmetic mean rather. So there are two kinds of averages. One is your simple arithmetic mean, and the other is a weighted arithmetic mean. So what is simple arithmetic mean and what is weighted arithmetic mean? So simple arithmetic mean is the definition that I have written over here. So summation x1 by n, summation xi. Now weighted arithmetic mean is written as x bar a weighted. So I'll write it as W over here. So weighted arithmetic mean is written as W1 x1 plus W2 x2 Wn x. All divided by, so if I write it symbolically, is 1 by capital N summation Wi x. So this is what the basic of average weighted average mean is, where the summation weights summation Wi is equal to 1. The summation Wi is equal to 1. Right, so this is called the weighted arithmetic mean. The next question that comes up to us is that why are we discussing weighted arithmetic mean? What is the area, or where is it that this weighted arithmetic mean is involved? So weighted arithmetic mean is a approach, or weighted arithmetic mean is used to calculate, or can be used to calculate, portfolio level PDs, right? Portfolio level probability of defaults. So I'll just log out from the screen and I'll be back. I think the screen has hung up somewhere. Yes, Srinivas. So Srinivas, there's a question over here. What is used in PD portfolio PD analysis? So I'll just come to that. Srinivas. Just let me log in into this softboard again, and I'll tell. So basically, for portfolio PD analysis, this approach of weighted arithmetic mean is used. Weighted arithmetic mean. Right. Now, when I talk about weighted arithmetic mean, so what we'll explore over here is the concept of portfolio PDs. So over here, first of all, let us define what exactly is a portfolio. So what is portfolio? A portfolio is nothing but it's a collection of loans. Is ideally it's a collection of loans. Collection of loans. Now, if I'm talking about collection of loans, so say for example, there are n loans which has been given out in a portfolio or in that particular portfolio, right? And once this loan has been given out in that particular portfolio, the next thing that comes to mind is that say for example, there are n loans which has been given out. N loans have been given out in that portfolio. Now, out of these n loans, say some m number of loans have defaulted. M loans M loans defaulted. Okay, so M loans have defaulted. So for each loans, so now, so suppose what I'm trying to do is I'm trying to predict the probability of default. So basically standing at 12 months ago, I'm trying to predict the probability of default. So obviously if there are M defaults, if M accounts default, so each of the accounts will have their probability, right? To default probability P1, P2, dot, probability Pm. Right. So there are M accounts and there are M probability of defaults. Now from here, what I want to do is I want to aggregate all these measures, all these probability estimates, and I want to report an aggregated measure of probability of default. Now one possible way is that I take up all the probability, I add them up and I divide it by the total number of observations. But that does not give me a foolproof measure, because when I am so basically when there is an aggregate measure, right? So after this aggregate measure, what happens is, if I take just the average of the probability measures, what will happen? That I will just it is like summation pi whole divided by n, but that may not be a foolproof measure. The reason is that along with the probability of default, something else is also important. The question that comes out is, what is important? So the more important part is not only the exposure, but the important part is also uh, the the it's not only the default chances but also the exposure associated with the default. Say for example, there are two accounts, right? Say account A. Now account A has a probability of default of say 0.08, or it has 8% chances of default, right? And the exposure that this account has is say 25,000. So if this account defaults in the next 12 months, the exposure outstanding is 25,000 and the bank will lose 25,000, or it has to recover out this extra 25,000. Then there is another account B, which also has 0.08 per point chances of probability to default, but the exposure that it has is 1.5 lakhs. So the question that comes out over here is that, are these two borrowers or are these two accounts of similar riskiness? From the chances to default, they may be, but if you look into the exposures or the amount outstanding, then this borrower is a relatively low risk borrower, whereas this borrower is a relatively high risk borrower. Because even though both of them have the same chances to default, but if this second borrower, if account B goes into default with that if that 8% chance realized for account B, it is always more threatening to the bank than for account A. Therefore, when you are computing, so if I need to report the overall probability of default for the portfolio, I just cannot report 0.08 divided by 2. I have to take into account the relative exposures of the accounts as well. So therefore, weights are associated with each of the probability of defaults. So the weights are exposure at default, the EAD for the ith account divided by the summation of EAD, that is the overall exposure. Now what I want to know over here is, that what is the relative exposure. So over here, this is the weightage that has been given to an account to do this. So what is this weightage or the weights that I'm talking about? The weights are nothing but these are relative importance. So This weightage is nothing but the relative importance which are associated or which are given to each observation. Right. Okay. So Srinivas has a question over here. Um, my PD for low exposure and his exposure are the same in this example. But why are we consider the EAD of 1.5 to be more riskier? Okay. So basically the idea is that if this account goes on default, say account A goes on default, right? So the account that goes on default, uh, so let's suppose there are these two accounts 0.08 and 0.08 for both account A and B. If account goes into default, the bank at max loses 25,000. If account B goes into default, the bank loses 1.5 lakhs. So therefore, the exposure that the bank has from account B is much more, right? So similarly, say for example, if there is my account in the bank and there is Mr. Ambani's account in the bank, if Mr. Ambani defaults and I default with the same probability, then in case Mr. Ambani's default case realizes, he has a greater exposure to the bank. I mean, the bank has a greater exposure to him through him than through me. Therefore, A is less riskier than B. Therefore, when we are trying to do the portfolio, we are trying to create the aggregate measure of or aggregate or a portfolio probability of default, then it is weighted by the relative exposures. So over here, what happens is, so PD over here will be summation of Wi, right? So this is what uh, estimate, or this is a way where the weighted average or the concept of weighted average is used. So this is just one of the ways. So similarly, weighted averages are used across different methods, right? Now averages or averaging can be used to smooth out fluctuations in a series of data. So that's the moving average application. So there are a lot of these different ways. So is this idea of portfolio PD and the weighted average clear? Now why weighted averages are used? What is the weight? So most of the cases over here you will see that the exposure, so each of the accounts are weighted by their relative exposures. Clear up to this point. So this is your portfolio PD. Okay. Now having discussed the basic measures of central tendency, The next measure that we talk about over here is the measures of dispersion. So what is dispersion? Dispersion is nothing but it's the measure of variability. Dispersion. So what is dispersion? So dispersion is nothing but the variability about the central measures. It is nothing but the variability about the central measures. The central measures. Be about the central measures. And the most basic measure of dispersion that we talk about is the standard deviation or variance. Or standard deviation. Right, so this is variability about the central measure. So variance, so this is nothing but, so two of the most well-known and widely used measures of dispersion is variance or standard deviation. And there is another measure, another very basic measure of dispersion, and this is known as range. Right, so range is another measure of dispersion. Now, apart from this, there are other measures such as you have range, you have the measure of the mean deviation. The second is you have standard deviation of variance. Then, so these together they comprise of your absolute measures dispersion. Together comprise of your absolute measures of dispersion. They are called your absolute measure of dispersion. Now, similarly, like measures of central tendency, measures of dispersion also are divided into two parts. One is the absolute measure, and the other is the relative measure. Right. So there are these two measures. So obviously, now after the absolute measures, yes, we'll come to discuss the relative measures of dispersion as well. Now, the relative measures will very much stem from the absolute measures like all other cases, right? So we'll just start off with the absolute measures and then come to the relative measures. So basically talking about the first measures of dispersion, that is range. Range is nothing but maximum minus minimum. Range is the maximum value minus the minimum value. So it shows the dispersion that is there between the maximum possible value and the minimum possible value, right? Now, the problem with range is, so one very advantage of range as a measure of dispersion is that it is very simple to evaluate. It's very simplistic in nature. So it is actually very simplistic in nature, in definition, in terms, and it is, it's very algebraically stable, and you can very clearly compute the measures and everything. It's simplistic and easy to compute, and easy to compute. Now the limitation with this is that range gets affected by extreme values. So it really gets affected by affected by extreme values. Right? So it's simplistic and easy, and it's affected by, and it gets affected by the extreme values. Now after this, so that is the reason why, I mean, you do not use range as a very critical measure of central tendency, but what you do in retrospect is, or rather what you do is, you report range, but for your analysis, you consider variances, or you consider variance or standard deviation. Now, apart from the fact that range is affected by, extreme values, range is another limitation. That is, it is not very representative because it takes into account only the maximum and minimum value. So it accounts for only max and minimum values. Only the maximum and the minimum values. So therefore, it's not very representative in nature. So you consider, so only maximum and minimum values are considered over here, right? Now, once this is done, so hence the point is it is not very representative. Not a very representative value, right? Now, once I have given way to this, once we have discussed it, the next part that we move on to is the measures of, and from there, we move on to talk about standard deviation. The biggest advantage of standard deviation is that standard deviation, or I mean, as a measure of variation or dispersion, considers all the values in the series, and it considers the deviation about the average value. So basically what it generally does is 1 by n summation xi minus x bar. So the first and the most important advantage is that it considers all observations in reporting the dispersion. Therefore, I can say that all the observations are concerned, or all the observations are reflected in the, or the entire data set or the entire distribution is reflected in reporting the measure of dispersion. All observation represented. The next part is it gives us an idea about the average variation that is there. The average variation, right? And the third that happens over here is that it reports the deviation from the mean value. So it reports deviation from the mean. Deviation from the mean. Right? So since it reports deviation from the mean, the biggest advantage is that if your mean, if your distribution is skewed and your mean is reflected, I mean affected by extreme values, that automatically gets represented in the standard deviation, since the average deviation, the overall or the sum or the average of the deviations tend to increase once the standard deviation, once this increases. So once the standard deviation increases, this thing happens, right? So the standard deviation helps us also, it would also help us capture the symmetricity of the distribution, because on one side, to the higher end side, the variation relatively lower, but the overall variation would actually increase in case of an asymmetric distribution. And that is where standard deviation comes into play. And since it's a square root kind of a concept, therefore, and square root followed, a whole square followed by a square root, standard deviation is always greater than equal to 0. You will never get standard deviation being negative, right? Now, using mean and standard deviation together, right? Using mean and standard deviation together, a measure of dispersion, another alternate measure of dispersion is actually reported. So that is called the coefficient of variation. So using mean and standard deviation, we also report another alternate measure of dispersion, which is called the coefficient of variation. Variation. So the coefficient of variation is defined as sigma, that is the standard deviation, divided by mean, which is x bar. So when I write x bar, I simply mean x bar a, or the arithmetic mean, into 100. So what coefficient of variation tries to do is, coefficient of variation, what it tries to do is, it tries to frame an understanding that, or so basically what it tries to do is, it tries to understand that how is the variation, or how much is the variation relative to the mean, and hence it is a relative measure of dispersion. So it tries to assess dispersion, relative to the mean, right? So this is a measure of, so coefficient of variation is a relative measure. It's a very important relative measure of dispersion. Measure of dispersion. So it's a very important, and yet this measure of dispersion is called the relative measure of dispersion. Clear on this? Now, okay, so up to this point, is it clear? Then I'll move on. Great. Great. Now the next part is, where do I use this coefficient of variation? Why would I need to do this? Now for this, let's think about a stock. Okay, so suppose there are two stocks, or there are two assets. So there is asset A and asset B. So asset A has a mean returns mu A, and asset B has a mean return mu B. Asset A has a volatility sigma A, and asset B has a volatility sigma B. So now the question that comes out over here is that I want to understand which one is to invest. In which one to invest? Over here, mu A is greater than mu B. Also, sigma A is greater than sigma B. Now what I want to do is, I want to compare that which is a better asset. Now if I look into mean returns, asset A in terms of mean return is always better, because the mean returns from A is greater than the mean returns from B. Similarly, when it happens from sigma A, then like the mean returns from sigma A is greater than the mean returns from sigma B, right? So over here, if I need to talk about, so basically it says that A has a greater returns, but also A is a more risky asset, because the volatility about the mean returns for this asset is also very high, right? So this is a more high risk asset, because not only it's not only is its mean higher, but also the volatility of A about the mean returns is higher. Similarly, over here for the low returns, so this is low risky, right? Now, how do I compare between the two? So what I do is I compare the variation of the first asset relative to the mean. So relative to the mean is the what percentage of the mean is the variation. So if the variation relative to the mean is higher for asset A, then I'll know that the asset A is more risky and the variance is much higher relative to the mean. Similarly, on the other hand, for the so basically, on the other hand, for asset B, if I see that the variance is relatively less compared to the mean, I know that then that's a relatively more stable asset, right? So over here, so what we do is we compute the coefficient of variation for both the commodities. So this is sigma A. Right now, after comparing, if I see that CV is greater than A, then I'll opt for asset B. If I see that this is the other way around, then I'll opt for asset A. Clear? So this is where, or this is how the measure of this, the measure of coefficient of variation is used to compare between two distribution and to understand that which one is a more risky and which one is a relatively less risky distribution. Clear? So suppose if you have two groups of borrowers and you want to understand that who is a relatively more risky and with a relatively less risky customer, what you do is you compare between their coefficient of variances, and you can actually frame an idea about who is a better and who is a more risky borrower and so on. Right? Now, after this is done, there is another alternate measure. There is another measure of relative dispersion. Now, like we get coefficient of variance or coefficient of variance from standard deviation of variance. Similarly, there is another alternate measure called the coefficient of range. The coefficient of range. Right. So coefficient of range is another measure of dispersion. So what it does is it is defined as max minus mean divided by max plus mean. Right. So over here what I have is coefficient of range is max minus mean divided by max plus mean, right? So this gives us a measure of, so basically max minus mean gives the difference divided by the sum of the two. So this is another alternate measure, but it is not a very it is not a very widely used measure. People generally report the range and they report the coefficient of variation among the relative measures of dispersion, right? Great. So we'll stop here for the day. I'll not take it up further. Tomorrow we'll talk about some of the how using these measures from our data set, how is it that we can identify data challenges, right? How is it that we can deploy them in the SAS framework, right? So like what is the what are the functions that we use, and what insights, how is it that we can frame insights about the behavior of a variable while we are working with it, what are the different variations that we can apply, and so on. So we'll talk about the applications of these measures, and from here we move to discuss skewness and kurtosis in tomorrow's discussion, and then from there if we finish that part, we'll start talking about probability theory. Right, so basically over here we are just talking about a data set, about a variable, and about a data set where you have all the variable values and everything. Then will introduce stochasticity into the variables, because incorporating stochasticity and understanding how to describe a stochastic variable is something which is really very important. Clear? Great. Okay, so Srinivas has a question over here. Yes, tomorrow the class will also be at the same time, Srinivas, and it's around 2 p.m. IST, and we'll meet back then. Okay, bye bye. Thank you. Thank you, Srinivas.